Right, can we all see this? Good, good, good. Okay, my name's Sebastian. I work for a company called On the Beach. This has nothing to do with any of that. So why being right is slow? And unfortunately much less contentious talk than it sounds. So really, the talk should be called Why Being Accurate is Slow. Since it's a lightning talk, it's not going to be slow, nor is it going to be accurate. So let's get on with it. So what am I on about? What am I on about? So creating fast, scalable, and accurate systems is not possible. It's not. It really, really isn't possible to max out each one of those segments on a chart. We have to make some sacrifices with the code that we write, and we have to make some trade-offs. We have to make some decisions, and it really depends upon the things that we value. So, I have an example of technology that you've probably all used, and you probably all use quite regularly, where this might be an issue, and where you might not have noticed this was an issue before. So, we're going to use a good old relational database. Fantastic relational database. The best one, if you ask me, MS SQL. Oh, you met me before my first love, John. You're creating an invoice system using MS SQL Server or equivalent to do so. You are beholden unto the fraud laws of the United Kingdom, i.e., if you get done, you get caught out, you get caught out. And you need to ensure that you have sequential invoice numbers. Now, the reason that I specified this is that if HM Revenue in Customs come a knocking, right, and you've got invoice number 1000 and invoice number 1069 directly after it in the database, then someone might be asking questions where invoices 1001 through to 1069 went. And they might be doing so justifiably, or something might have gone wrong. So we don't really want the rothers coming after you. You missed my little policeman. There we go. Right. So, what's happening? Well, we've got a little SQL bit. So what I've done, put together a little bit of SQL just to represent a very, very simple invoicing system. So if you've not read SQL, we'll go over it a little bit. So we have a table of products, which has an ID. Now this is what you would call a surrogate key. It doesn't really mean anything, it doesn't really matter. All it is it's a monotonically increasing key. So it starts with 1, next one's 2, one after that's 3, etc., etc., etc. Yeah? We've got our invoices, which is very, very much the same as our products, and we have an intermediary table of invoice and products in which you have your invoices and your products tied together, because obviously you can have many, many products on a single invoice. Now, the first thing we're going to do is insert a couple of test values in there, because why not? Because we like to have fun. And from there, we would end up with an invoice table with 3 rows in it. Do we all agree? Fantastic.
There's no semicolon.
It is recommended, it is not required. So wind your neck in. Okay, so we have our 3 rows. So what do we do now? So we're going to start a transaction. Love the transaction, we like transactions. If you don't know what a transaction is in the database, essentially what it does is it creates a commit log of the things that you're doing, and only after you say, I want this to be applied to my database, does it actually go into the table itself. Otherwise, we can sort of roll it back, we can make sure that we can undo everything that we did in the first place. So what are we doing from there? We've added a bunch more values. We have 6 rows in there, all very sensible. We can all see what's going on. But what if we roll back here? What happens if we hit rollback at that point before we commit our transaction? Well, as we would expect, we end up with only rows 1, 2, and 3 in the database because they were committed initially at the start with the rest of our table creation. We inserted them straight away. But what would happen if we were to attempt to insert more values into our database at this point? What would happen? Well, as you might be able to see, our sequential IDs go 1, 2, 3, 7, 8, 9. Because actually, what SQL Server has done, and probably rightly so, is they have not made the primary key monotonic incrementer, the sequence, that backs that transactional. They've decided not to, and the reasons they've done that are really, really good. If you wanted two different transactions to add rows to a table at the same time, they would not be able to actually go and grab those IDs from the sequence without waiting for every transaction which is going to modify that sequence to commit. So you could be waiting behind half an hour's worth of hilarious data analysts' horrible query just to insert a single row into the database, which we wouldn't want, would we? But this is why generally it is recommended that one would not use a surrogate key in order to identify a row in a database when we're talking about something that's so important. So, with this kind of stuff, everyone says, well, it's a scaling problem, isn't it? So, it's just that we can't scale big enough. So let's just move to the cloud. Everyone likes to move to the cloud. We've got infinite scale everywhere if we go to the cloud. So messaging technologies are similarly limited in what you can do if you want to be fast. If you are using messaging clouds in the database, in messaging technologies in the cloud, they have the same principles behind them as databases do. If you want accuracy, if you want ordering, and if you want things to happen in a specific sequence of events, you cannot expect that with any amount of scale that is not a single point of bottlenecking, essentially. So trade-offs are made between accuracy, ordering, and scale always. And at times like this, I really just wish that someone had come up with some kind of defining theory for this as to, why this happened. Oh, CAP theorem. With databases and data exchange and storage technologies, and if you think about a messaging queue, you can think of it as a stream of data. You can think of it as a store of data if you're using certain ones like Kafka and things like that. And you have to remember that you are always making trade-offs between consistency, partition tolerance, and availability. And the one we're missing here for the most part is going to be consistency. We cannot ensure that the things that are happening are going to happen in a certain order. So, if you want a globally respected ordering key, you're going to have to introduce a bottleneck into your system. And this is what we have to do. If we want this, you have to bottleneck your system if you want any kind of repeatability and ordering and defined ordering in a system. You have to introduce a bottleneck. It's a bit of a cop-out. So what else can we do? What else can we do to help mitigate these issues? Well, event-driven systems can use an event-carried state transfer pattern. John works with me, he's heard me go on about this loads. So what you can do there is if you are adding events into a system, so if you're using some kind of domain-driven design, things like that, what you can do instead of saying, okay, let's create an item, and then if we want to modify that item, we'll pass the delta with just the change that needs to happen in order to get to the current state. What happens if your update comes in after your insert? Well, if that doesn't exist, then you're not going to be able to update a model. You actually are going to lose out on that information if it came in afterwards. And this can be a real problem for some systems where they require that correctness, and they sort of require the throughput that can be given to you by distributed systems, but they sort of can't guarantee the order in which things will be coming in. So you can use things like the event state carried transfer pattern, whereby you actually pass the entire object model as it comes. So every time you do an update, you emit an event that says the object now looks like this in its totality. And what you can do is you can actually look at, okay, when was the last emitted event? So when it comes in, you say, I've already got a version of this, and it's newer than the one I just received. Therefore, I save the newer one. Things like that. So that's an upsert pattern, a pattern of upserts in which an insert and an update are kind of the same concept. Essentially, if you get the later version, you insert it as an upsert. And you can also do the reconciliation here on the application layer level, which is a very similar sort of concept in which sort of when you get it, You decide what to do if you get something out of order. If you've already seen something, or if you've seen something twice, because most of these systems also cannot guarantee only once delivery. They will often guarantee at least once delivery. So you will definitely get it at least once, not in the right order, and not necessarily in the right, not necessarily only once either. And you can also just not care. Now, there's some really good cases for not caring, and this is where the data is going to be a drop in the bucket, really, where sort of logging systems, for example, where you're only ever going to be sort of getting large trends from the data, so logging systems and data warehousing and things like that, where the gist of it is a lot more important than the actual nitty-gritty of it. And so it's systems like these where it's a lot easier to sort of go, we don't care. It doesn't matter if we get it twice, doesn't matter if we get it out of order, as long as we're generally in the right ballpark, we're happy. So yeah, questions in that. And I do have a disclaimer that I do not guarantee the correctness nor accuracy of the answers nor the order in which they will be given. So, no? Fantastic. Thank you very much.